Let's welcome Rémi Bouzel with Challenges of Live Environmental Footprint Reporting.
Thank you very much. Hello everyone, so very happy to be here today with you. And as it was said, today I'm going to discuss with you about carbon footprint reporting and like the challenges that as a cloud provider or as a data center you can meet and how we solve them. So I'm Rémi Bouzel, I worked at Qarnot as a scientific director. I've been working there for 5 years now. And first I'll introduce you Qarnot very briefly. Then I'll dive in like the different challenges that I want to share with you. And finally, I'll try to discuss like some openings and some call to actions with you guys. So first of all, what is Qarnot? So we have a beautiful stand outside if you want to visit us. But basically, we're a cloud service provider, and we have like a few specificities. Of course, one of them is that we're based on OCP. Another one is that we really focus on reusing the heat generated by the servers. So to do this, first we install our servers or modules directly in places where the heat can be, where the heat is needed. So we won't install them necessarily in data centers, but we might install them in district heat network, in big swimming pools or in big industry, anything that has like a high need of heat and a constant need of heat. And of course, we also had to design our own module to really optimize this reusage. So that's the one you see on the picture with some OCP blades, and that's the one that's outside, of course. So as I say, we're a cloud service provider. Here, of course, we have like a user interface to spawn your batch jobs, etc. And what's very important for us and for our end user is that, as I say, we're like very low carbon. It's good to know it, but it's also better for our end users to show some metrics. So we designed these carbon facts that you see on the right of the screen. They're based on the nutrition facts label. And the idea is that for every single computation run by one of our customers, we share like the energy that was spent, the carbon footprint it corresponds to, maybe the PUE, WE, and we try to compare like what you saved compare with a regular data center, for instance. So that's our idea, and that's why it's so important for us to have like this live, almost live carbon footprint reporting. So now, what are the challenges? What did we face when we started this thing? So there are two main ones. The first one is more like a methodology. So you have to choose how you count the carbon footprint of your electricity mix. So let's say I install a data center in Lisbon here. Maybe the most intuitive methodology is what's called location-based. So I'll consider that the electrons that flow to my Lisbon data center, of course, they've been generated by generators nearby the city. And I'll just look on the internet, what's the carbon footprint of the Lisbon electricity mix, and I'll take this and include this in my computation. That's great because it's very intuitive and it follows the physics, so it's always pretty good sign. But then there's like a different methodology that is more and more developing and that you probably heard of, that is called market-based. So the idea of market-based is that each time a renewables generator emits energy and produces or injects some electrons in the grid, it also creates certificates. So in Europe, we talk about renewables energy certificates. In the US, it's called guarantees of origins. And the idea is that if my data center in Lisbon, it will still like the same electrons will flow through it. But I can buy these type of certificates. I can buy a certificate that was produced in Iceland, for instance. Of course, there is no way like the Icelandic electrons go through my data center. But because I bought these certificates, and that's a different market than the electricity market, because I bought these certificates, I can use in my methodology the carbon footprint, the Icelandic carbon footprint. So what's a bit weird is that it's completely counterintuitive because it doesn't follow the physics. But what's quite positive is that it helps funding the renewables because I have to buy these certificates. So these are like the main options, and now there's like a kind of a third way that is a bit in the middle that's called like 24/7 market-based. And the idea is same as market-based, but instead of looking for certificates emitted in Iceland, I will try to force myself to buy these certificates from renewables generator that are in Lisbon or in the Lisbon region, and that are emitted at the same time. And the good thing is that it follows a bit more the physics, so it's nice. And of course, it still helps funding the renewables, and actually even a bit more because it makes the price of these certificates grow. So that's like the first question that you need to ask yourself when you're doing this. At Qarnot, we do location-based because we want to follow the physics as much as possible, but these are basically the options that you can see on the market. And by the way, because I know that for data centers, we hear a lot about PPA, so PPA is based on this. You can buy like electricity and sometimes certificates as well at the same time. So that's the first challenge. The second one is a bit more, let's say, technological. It's about instrumenting, and basically, once again, you have two options. First one is a top-down approach, meaning in your data center, you will have some sensors that are high level, maybe at the level of your electricity arrival. And in this case, if your goal is, as it is like Qarnot, to give some like precise feedback to your user for each of their usage, in this case, it means that you have this big sensor and you have to find out basically, okay, this customer used this amount of vCPU, and you try to weight like based on this sensor all your users' activity and try to tell every user roughly how much they use the energy. What's good is that it doesn't cost much money because you already have like these sensors. What's less interesting is that you cannot offer like a high precision, high granularity to your users. So of course for Qarnot, we want it to be like as precise as possible because it's a great added value for end users. So we went for the other option that is bottom up. That means you need to install sensors as closely as possible to the unit that makes sense to the user. So it can be the servers if you're doing bare metal. If you're hosting some virtual machines, then you probably want to have like a virtual sensors in your virtual machines. So you have all these options. At Qarnot, we don't do multi-tenancy, so what's interesting for us is to have a wattmeter in an ideal world, a wattmeter for every single server. And of course, it's better because it's more precise, but it comes with a cost. You have more sensors, you have more operations to deal with. So that's what we want to do. But in the real world, you, of course, don't have a wattmeter behind each server. And for us, for instance, sometimes we have a wattmeter that would include the server and the power supply. That's the ideal world. And sometimes we just have access to the BMC, so basically the consumption of the motherboard. And sometimes we just have access to RAPL. So RAPL, you probably know, it's a module developed by Intel that gives you basically the energy consumption of the CPU and the RAM. So sometimes, each case, we would prefer to have the wattmeter, but sometimes we don't. And so the idea for us, we had like a project around this, was to say, okay, when we have access only to RAPL, are we able to simulate what a wattmeter would have given us with high precision? And same if we just have access to the BMC, can we, like, do we have a function that is precise enough to give us what a wattmeter would have given us? So we set up a test bench with all these meters, all these sensors on the same server, and started to run some payloads. So here you see like the power consumption as a function of the time, just a random payload on the left-hand side, and the right-hand side is some stress test. So the idea was to stress every hardware resources that we could. So of course the CPU, the memory, but also the disk, memory bandwidth, etc., etc. Stress everything to have as many points as possible. And well, first result, it's reassuring. Yeah? We see that RAPL power consumption is lower than the BMC. It's normal because it takes into account less stuff on the server. And BMC is less than the wattmeter, which makes sense as well. So then we tried to draw and to see if there was like an easy function to express RAPL in function of BMC and BMC in function of wattmeter. And the good news is that it's almost perfectly linear. So that's very reassuring for us. Because what it means is that if we just have access to the RAPL sensors, we can like very precisely tell what the BMC would have given us. And it's interesting to have this curve. It's experimental. We also wanted to make sure that it follows the physics and that we understand where this curve and this coefficient come from. So these are speculations, but from the specs, from the specifications of the OCP servers, it's like it matches these coefficients. So we have like a specific slope on the rope, and roughly corresponds to the voltage regulation module of both CPUs and RAM. So that's set, it's understandable. And then we have an offset on this curve that corresponds to the network card. We have like very small fans. We replace the OCP fans. We have small fans, so we add this, the fans, the SSDs, and we come to roughly this 27 offset. So we have this expression of BMC in function of RAPL. We did the same for a wattmeter and BMC, and once again, we have like a nice linear relationship that is great because then it means that if we only have access to the BMC, at the end we can access the wattmeter results. So that's exactly what we are looking for. And once again, we try to check that it follows the physics. And actually, we had some help as well of OCP members discussing this. And we see that explaining like the losses in the power supply, in the BMC, etc., we match these numbers pretty well. Finally, so we did this with like a single server type. Then same configuration, we took several servers. And as we know, like you have like some slight differences. So each color on this is a different server of the same configuration. So you see it's always linear, but you have like a small offset between them. It corresponds to what you find in literature of like a 5 up to 10% sometimes of uncertainty because of manufacturing small differences. So that follows, and like we understand this, and then of course the follow-up of this is to do this on all the configurations that we have at Qarnot. So that's what we did, and thanks to this, and because we have like this heterogeneous instrumentation, we manage on all our part to be able, for every computation, whether we measure BMC or RAPL or have a wattmeter, we're able for every computation to say, okay, to the end user, okay, this consumes this amount of energy, this corresponds with the location-based methodology, this corresponds to this amount of carbon footprint, and you saved this amount because the heat was reused. And now, of course, there are like a lot more that we can do and that we hope to do with OCP. And there's like probably two main ideas or things we'd like to push and to participate in at OCP. The first one is basically not only focusing on carbon, because everything I mentioned today was about carbon. We know that water usage is like something very important in the DC world. So historically, we reduced the PUE a lot. We increased a bit the water consumption. So now the idea is like maybe the more we integrate metrics that we follow, the more we'll be able to do good in all these different factors. So here I just mentioned 3 of them, but I could add like, I don't know, land acidifications, et cetera, et cetera. You have a lot of them, so there's probably a discussion to have for which one are the most relevant, on which one do we have some data that we can play with. And at least, I guess, water usage nowadays is more and more like documented. Abiotic depletion, that is like stating the fact that we don't have an infinite amount of copper, of aluminum, etc. on Earth. This is starting, but still there is no like solid methodology yet. So I guess OCP could tackle this issue. Maybe it already started, and we'd love to be part of this and work with you guys on this. So that's one way to go further than what's actually done, going further than carbon. And the other way, Cloudflare just mentioned it before, is going further than scope 2. So today, before I just spoke about scope 2, the usage and like all the electricity and carbon footprint emitted during the usage phase of a server. But what's very important as well is to consider scope 3. So scope 3 is, as it was mentioned before, everything else. And basically it includes essentially manufacturing and end of life. End of life, honestly, today, even the research, like there is very low information. So most people are focusing on manufacturing. And there is, of course, a lot to say. So manufacturing, you have to picture all the energy that's used to mine the different components. Then you need to refine them, you need to transport them, to assemble them. So that's all this energy. That's a huge piece in a server. And here we compare so these are full life cycle analysis of the same server, but with 2 different countries. So in blue, you have scope 3, so manufacturing, and in green, you have the usage. And you see that in some countries, so country A, for instance, has a high carbon footprint electricity, so the usage is comparatively very, very big, so it's 3, 4. So, and like, if you look at this, you say, okay, let's focus first on the usage. But if you're in country B, so for instance, we're based in France and we have operations in Finland as well, so the carbon footprint of the electricity mix is very low. And so you see that manufacturing is definitely, for us, the next challenge. So we reuse the heat, so it means that we managed to reduce scope 2 almost to 0. It's never 0, but almost. And now like our real challenge is how do we manage like this big scope 3 circle. And of course, it's very difficult for 2 reasons. First of all, today, we don't have much information. We don't have much information because manufacturers don't share a lot, and I assume they don't share a lot because their own providers don't have much information. So I'm sure like OCP is probably a good place because you have like so many different companies and interests. It's a good place to discuss this and try to move forward. I guess as a community, that's where we'll be stronger, and that's this type of topics that can be tackled here. And another one that is that the small amount of data we have on this topic comes with a very high uncertainty. So sometimes you can have like data and you know that maybe you have like a 50% uncertainty. So it's very difficult to draw conclusions from this. So to sum up like these, the two maybe ideas that we can push and that OCP can push and that Qarnot definitely will work on this with you guys is first going further than carbon, and two, going further than scope 2 and including scope 3. And of course, there are already some work streams working on this that we started to join, and we'll be happy to participate even more to the OCP community. Thank you very much.
Rémi. We do have a few minutes if anybody has a question they would like to.
Hey, I'm Andrea with Schneider Electric. Wondering, how are you delivering that that label that you presented to customers?
What do you mean, which technology?
Right at the first is like the
methodology?
nutrition label. How are you delivering that? The carbon facts.
Are you mentioning, like, are you talking about the methodology that we use or how we share it with the
Yeah,
users?
the communication of it.
Okay, so here that's like a screenshot of our platform. So we are doing batch computing jobs. Every line is like one single computation, and if you click on it, you have all the details. And among these details, you will have like this nice carbon facts, and you'll have like some extra explanations to do some pedagogical work for those who are interested in.
Nice. So everybody has a Qarnot account, probably, right? And that's like their dashboard?
All our users have, yeah.
Yeah, okay, that makes sense. Thank you.
Sorry if I missed this, but I'm wondering if you have any telemetry from the generator. So let's say there's a PPA contract with a clean energy generator to track how much they're generating throughout the day or throughout the week, or do you assume like a constant factor for an intermittent resource?
So today we use the location-based approach.
Okay.
And so you have like two choices basically. Either you take an average, either, I guess in most countries and sometimes even at the region granularity, you have some APIs that are almost live that will give you the carbon footprint of the electricity mix. And I assume for, if you contracted with a generator, I guess it depends on the generator, but I'm sure that some of them would be able to give you this.
Thank you.
Who's first?
Hello, thank you, great talk. I wanted to ask about the BMC specifically. So which sensors are you using? Because I know that most of the BMCs have the connectivity to the PM bus on the power supply. So based on that, you probably could have something similar to the wattmeter that you are talking about.
Sorry, what sensor are you mentioning with the power
Which
supply?
sensors are you using from the BMC to estimate the power consumption?
Oh, honestly, I'm not sure. If you come to our booth, we can ask our guy who's
Sure.
more specialized in this.
Okay, thanks.
Okay, and last question here.
Hi, I'm Jeff with iMasons. Could you go back to the slide with the nutrition label, the carbon facts?
Yes.
I was curious, the top number there, 17.11, is saved carbon footprint. I was curious about that. When you buy a thing of a loaf of bread and it has nutrition facts,
Mm-hmm.
it's the carbon, it's the nutrition of the loaf of bread. This is something else. This is not
It's
the
a free
embodied
adaptation
carbon
of the
in
nutrition facts.
server. It's what are you reporting here?
So, I won't go line by line, but basically there are two pieces of information that are important for our users. First, the carbon footprint that will correspond to the nutrition facts of your loaf of bread. And secondly, what they would save compared to like an average scenario. That is, I think in this case, data center with a PUE of 1.2 in Europe.
So rather than saying what the carbon content is of your product,
No, we do both.
I don't see saved carbon footprint.
Then the details that maybe you cannot see here, but the first line of carbon that corresponds to what's emitted. Of carbon.
Numbers.
Yeah, the smaller
numbers are
numbers.
the carbon, and then he calculates the savings
Ah.
at the headline.
that's an interesting way of relating the information, rather than what you actually contain, what you assume is
But-
different from what they might have eaten instead of eating your loaf of bread. They
Yeah.
might have eaten a Big Mac, but they didn't. I don't know. It seems an odd position of the information.
But it's because this piece of information by itself is difficult to interpret if you don't have like a mean of comparison. So that's why we put this one forward. And then, of course, they have all the details if they want to compare the figures.
All right, thank you, Rémi. We are out of time. If you have any questions, feel free to grab Rémi.
Thank you.